make this compound. Instead of the 2-bromobutane. What would be very different?
Water.
Do I add water? Well, how would I add water? Where? So what's going to change from what I have up here? Where am I going to branch off to something different? I still have 4 carbons, so I still have to join 2 chains together. So all of this perfectly usable until I get to this point. It was at this point where I then took the triple bond and turned it into the bromide. And so I can do the H2 and Lindler and get down to this. And now what would I do? So the only change is the last step. And the last step would be to make that stuff right at the same thing. And do that. And how do I do that? This is an anti-Markovnikov addition of the H and the H. And that's one of the few that we have, those few complementary pairs we have to do Markovnikov and anti-Markovnikov. So if I put a bromine there at the end and said make 1 bromobutane, you'd be in trouble. It would be a lot more complicated if you could do it at all to try to put the bromine there. You certainly couldn't take this apart because you'd get to the end, you'd end up with the double bond, and when you try to put the bromine on the first carbon, that's anti-Markovnikov, and you have a problem. However, that problem goes away, and the way in which you're going to do that next semester, well, there's 2 ways you're going to do it next semester. You'll see when we begin chapter 11, which we're going to do very shortly. There is a reaction, and it's a relatively trivial reaction, that will turn an hydroxide group in a molecule into a halogen, like a bromine or a chlorine. And so if you had to make 1 bromobutane, you could make the alcohol, because you know how to do that anti-Markovnikov, and then turn the OH into bromine. And it's a 1-step reaction. So that is a pattern you're going to see a few times next semester. You'll get to some point where you want usually a halogen in an anti-Markovnikov position. There's no easy way to get it there based on the chemistry that you know. So make the alcohol and then turn the alcohol at the very end, replace the OH group with the bromine. There is, and this is where I'm going to give you a little bit of a leg up on the other 2 classes, because I don't think Mike talks about it, or Catherine, because it's not in the book anymore. It was in the book at one point, and then it disappeared. There is an alternate reaction. If you remember it, fine. If you don't remember it, you can still survive. But basically, it is possible to take an alkene and end up adding H and Br to that alkene in the anti-Markovnikov sense. So there is a complementary reaction to the bromination of an alkene that will give you the anti-Markovnikov product. The reaction is, it works only with bromine, however. Don't try it with chlorine. It works with bromine. And the conditions to do this are to use add HBr, because that's ultimately what you want to add to the double bond. But do it in the presence of peroxide. 2 things should be readily apparent by what we just talked about. Since you get the anti-Markovnikov product, this thing cannot possibly go by the carbocation mechanism that we saw. So it's not a polar addition of HBr to the double bond. mechanism, we know the mechanism, again, you don't need to know it, but the hint to the mechanism is the fact that you're using peroxides. Peroxides are notorious free radical initiators. Peroxides are things that have an oxygen-oxygen single bond that bridges two groups together. This bond is a very labile bond. That bond breaks fairly easily to give you two oxygen free radicals, and that's what it takes to get this reaction going. So, adding HBr to a double bond in the presence of a peroxide goes through this alternate mechanism, and if you remember, it goes through a free radical mechanism, which means it's going to pull a hydrogen off the alkene, basically make a free radical out of it, and then that will add the bromine. If you think about it, the stability of free radicals is the same as the stability of carbocations. So it seems a little strange that this would reverse the stereochemistry of the reaction and give you an anti-Markovnikov addition as opposed to a Markovnikov addition. And the only reason it does that is because when you do the addition of HBr with peroxides present, the two things, the H and the Br, add in the opposite order. When you did the straightforward addition of HBr to a double bond, the H adds first, which means the dot ended up on the more substituted carbon, and so that's where the bromine ended. In this case, the bromine adds first, and it goes to it gives you the dot on the more substituted carbon, and then that picks up the hydrogen. If you're interested in the mechanism, come talk to me. I'll be happy to show it to you. You can figure it out on your own, especially now that you know that key piece, that the thing adds in the reverse direction that the normal HBr does. But this is a useful reaction to use next semester. So when you get to the point where you end up having to make an anti-Markovnikov addition of bromine to a double bond, you can make the alcohol and then replace the OH, so do a two-step reaction at that point, or show either Mike or DJ, whoever's teaching the class, how much you know, and throw this one in there. So it's a useful reaction to have around. One that at least I know Scott gave questions that utilize them, could utilize this thing a lot. He's not teaching it next semester, but I doubt DJ or Mike's class will be that different. All right, that's synthesis. I could do 15 more synthesis problems with you. It doesn't help. It's watching somebody play basketball. Watching somebody in the NBA play basketball. You don't learn how to play basketball that way. You gotta pick up the ball, get out on the court yourself, get bruised, and try yourself. So that's what we'll do tonight. Bruise you a little bit. Ask you to do some syntheses. I'm going to give you a whole bunch of them. There's no way you're going to finish them tonight, but just consider this a multi-day worksheet and finish them all off, certainly before our next exam, which is a week from Monday, where you will see those syntheses come to life in a more critical way. All right, so that's it in terms of alkynes. I want to, before we start spectroscopy, do this very short chapter, which is chapter 11, I believe. Yes, it's 12 is spectroscopy. No, this is chapter 10. Right. Keeps changing the chapters around. 11 is what we're going to come back to. We're going to finish the semester with 11. And I promise you there are no new reactions in chapter 11. So after we do 3 or 4 more now, you're done learning new reactions. Chapter 11 is all about how a lot of these reactions occur with alkyl halides. So alkyl halides is the subject of chapter 10 and really 11. But 10 introduces these as a functional group. The key thing about an alkyl halide is the polarity of the carbon-halogen bond, where the carbon has a small delta plus charge, the halogen has a small delta negative charge, depending on the electronegativity difference between the two. We've already done a lot with alkyl halides during the course of the semester in terms of making alkyl halides, preparing them, synthesizing them, whatever you want to call it. we saw that you could take an alkane, take a halogen, shine some light on it, and you will get alkyl halides. The problem here is that you typically get multiple products. You might get monobromo or monochloro, dichloro, trichloro, and where the halogen ends up can be problematic to control depending on the alkane that you start with. More reliably, in the alkene chapter, we saw that if you take an alkene, you can turn this into an alkyl halide in two ways. You can add halogen to it, either chlorine or bromine typically. Fluorine works, but it's usually explosive. Iodine will work, but very slowly. And what you end up with is the dibromo, in this case, or the diallo compound. Which will always be a trans or an anti-addition of the two halogens because of the formation of the intermediate, which is the bromonium or the halonium ion, or chlorine, which kind of bridges one side of the carbocation and protects the other. We can do the same reaction with a hydrogen halide to add only one halogen. It's done there. There. Right way, I should say here, you'll get this product and the enantiomer. So there really will be two products of that reaction. And you realize that. Depends on what the question asks for. With the HX addition, you're just going to end up with the halogen and the CH3 will be on the same carbon. And in this case, that's the only product, since there are no chiral centers in there are no enantiomers. But you will get the X attacking from both the top and the bottom. So you get both possibilities there. If there was another group on the ring, which would make that a chiral center, you would get a mixture of that and its enantiomer. And the last way of doing it is the new way, which is introduced in this chapter, which is, let me use a nice symmetrical one for now. Take an alkene and treat it with NBS and shine some light on it. So we're shining light on it. That immediately tells us this is probably some free radical mechanism. What's NBS? Anybody remember? You've seen this once before. It's N-bromosuccinimide. I don't care about that. You just need to recognize it as a reagent and realize that it is effectively equivalent to Br2. It is the compound that decomposes slowly and releases Br2 in the solution. It has solubility advantages because it's more soluble than bromine would be in most of these reaction conditions. NBS looks like that. And again, you don't need to know that, but you should know when you see NBS, it's the way of adding bromine to something conveniently in terms of solubility, and also making sure that there's never a lot of bromine around because it releases it slowly. And that's important here because you only want the monobromo product